Cool. Right. People are rolling in now, so let's get started. So yeah, welcome everybody to today's webinar. We're going to be talking about the release we've made at Encord of what we're calling EMM1, which is the world's largest multimodal AI dataset. A really big dataset, a really big announcement as well for us. My name's James. I'm the VP of Engineering here at Encord, leading our engineering team building out our product, and joined today by Fred, who I'll give a quick introduction to himself as well.
Yeah, hi, I'm Fred. I'm leading the machine learning team over at Encord. And so I've also been leading this project on creating this data set and also actually using it a little bit. And we'll see that as well during this webinar.
Nice. So what are we going to talk about today? So today it's not a product pitch. We're not going to be talking very much about Encord's day-to-day product and the thing that we're working with our customers with. We're going to be talking about this data set, what we did to build it, the value that it can hopefully provide, why we made it open source, and hopefully provide some takeaways about data, about tooling, about how the data set can be useful to lots of people in lots of environments and lots of experiments as well. Just quickly though, so you have the context. So who are Encord? What do we do? So Encord is an AI data company. We're building the multimodal data platform for AI. So that's a software platform that allows you to understand and build and annotate your AI data sets, helping you curate unstructured data before it's been annotated, helping you annotate data across many different modalities: image, video, medical image, text, documents, audio, physical AI data, such as from LiDAR or from self-driving cars or from drones, and then helping you use that data to train, to align, pre-train and post-train your AI systems, and also to provide that data to the systems when they're deployed in production and understand their usage of that data as well. That's what we do as a business. But enough about that. We're going to hear a lot more today about the data set and about why we launched it. So let's get into that. So Fred, you're going to be doing a lot of the talking here. Let's start by laying the groundwork and the motivation here. Why did we go and build this multimodal data set?
Absolutely. This is perhaps the most important question, I guess, at least to get us started. And there are a few reasons. One of them is just an observation of where the field of machine learning and AI seems to be going, where all the money is flooded, and that seems to be towards this multimodal direction. It can be multimodal in many ways. It can be in like physical AI, where you have robots that needs to understand many different modalities, or it can be more LLM kind of multimodal, where you have LLMs that you're still chatting to them, but maybe they need to understand more modalities. And the final one is actually all these generative models, right? We have seen problems solved recently, like lip syncing, for instance. There are many problems that kind of they're sort of inherently multimodal. And so one of the observations we did was that there's this model called CLIP. It's from OpenAI. It's actually kind of in, I guess, at least in machine learning sort of timeline, it's pretty old. But it has powered so many applications already. And of course, it's been sort of improved in many different ways. And I'm just gonna say CLIP and just like think of all the different contrastive models, really. So we brought up a few examples here, but that's really the second part of sort of the motivation is, I think if we can build a good data set, truly multimodal, then we can actually empower a lot of applications downstream on top of this data set. So let me just mention a couple of them here. One is with CLIP or other of these contrastive models, you can search databases based on natural language. That is what we do when we do kind of a natural language search. That's typically what we call it. I can type a piece of text, and then I can find images that relates to that text. That came from data sets of images and their alt text probably, or surrounding text from an internet. Training on the entire internet of those kind of images gave us a CLIP, essentially. Then that particular model CLIP, or one of the other ones, can actually also be extended to do image captioning. It can also be extended, for instance, put into a stable diffusion to do image generation from text. So kind of this same embedding space powers all these different applications. The last one we have here on the slide is zero-shot classification, which basically means I have a problem where I don't have a trained model already against labels for classification. Now I can just embed the names of all the classes in my classification problem. And then I can embed my image, and I can compute a similarity between the image embedding and these class names. And then I can actually make a classifier without training anything downstream. So there's so many, and this is just some of them. There's so many applications. And now imagine taking that and making it truly multimodal. That's really the second motivation here.
And that's why multimodality here is so important, right? I think in my view, at least, a big part of the reason as to why this LLM boom has happened in the last few years is because there is a huge amount of text data available, right? Which is the internet and all of the books ever written and all of the articles ever written that was available to help pre-train systems to predict the next token of text. But a lot of the real AI systems we're trying to build are natively multimodal. They need vision, they need to hear, they need to interact with the world. And there isn't this same internet of multimodal data there waiting to be mined. It's a bit more complicated, but that's what this data set's here to do, right? To provide that very large starting point for the training of systems, not just to predict text, but to predict data across all sorts of modalities. So let's talk about the challenges then in building this data set, why that's important. Tell us, Frederik, like how is it difficult to kind of build these more modalities in?
Yeah. So I kind of drew this this chart by hand. So don't use your ruler and kind of try to infer anything in particular from it. It's more to sort of like get a point over the counter here. And the point is basically, if you look at this chart, it's meant to show that if you want to have very large scale, it can be very hard to get many modalities. So I can see that by looking at small dots. So the smaller the dot, the less modalities. On the other axis, on the y-axis, we can see this sort of quality thing here that if I can get like a high quality, and again it's like either I get one or I get the other, so they're kind of inversely correlated. So that's, you can see this kind of trend that it's showing the graph. And so what we really wanted to do was trying to sort of at least push towards the upper right corner, right? Get more modalities and get a like high quality. And so there are a lot of challenges in this sense. Some of them are just like finding good sources of data. For some types of data, like we talked about the internet, right? Some types of data is very easy. Image and text together is very easy. You can also get like images and audio can also somehow come together if you look at videos. But finding, for instance, 3D objects and audio, something that never sort of naturally appears, at least not in what you can scrape from the internet. So for that, we had to actually build our own data set to get that type of data available.
Yeah, so we've actually got our first poll here as well, which you can launch now, which is asking you what are the biggest challenges that any of the listeners have had for building their own multimodal data sets. So drop your answers in there. I think in particular, having just so many modalities at once, right, and building those relationships between the two. There are lots of multimodal data sets with 2 modalities or 3, but going from to image, video, text, audio, and 3D models, 3D objects is the particular challenge here.
Yeah, absolutely. I'm not aware of any open source data sets actually whatsoever for all the 5 modalities.
Nice. So with that in mind, what are we announcing? Let's play the video, and Frederik, you can tell us a little bit about what we have here.
Yeah, absolutely. I don't know if maybe yes. So we built a very, very big data set of groups of all 5 modalities. This is very, very useful for doing what you would think of as pre-training in LLMs. And we have further elevated a subset of this data by a lot of human work, hard human work, blood, sweat, and tears, I guess, to get a very high quality on some of the data as well. And you can think of that as like a supervised fine-tuning or like a post-training phase type of data set. And then finally, we've also built an evaluation data set for a particular subset of this problem, because that was also not available anywhere. open source.
Nice. What are the we'll go into this in more detail, but what are the use cases that potentially jump out to you, Fred, as ways people can use it?
Yeah. So the first and most obvious use case is to build a clip model, but for all the modalities at once. And we already somehow showed how you can do that, in the sense that we've already built a model, and we'll actually see it in action a bit later. But that is one thing you can do. You can take all these groups and use them in a contrastive manner to build these contrastive models. There are also many other use cases. You can similarly take this data and then fine tune an LLM to understand all these different modalities as well. That's been done many times in the past for instance, computer vision. You can do the same thing here. So you can actually now let your LLM understand more modalities. So 3D objects, point clouds, or audio as well. And then, of course, also like we kind of touched upon some of these problems in the past, but also generative models that you can, for instance, condition on a particular sound or a particular structure of an object.
Nice. Well, I think without further ado, then let's go and explore the dataset in a bit more detail. So, as well as releasing it to the public, we've also released an interface where people can go and explore the dataset and view its items and do some searches there as well before downloading the whole thing offline. And Fred's going to give us a bit of a demo now about what that interface looks like, where we can explore some of the dataset in real time. So, over to you, Fred.
Thank you. Yes. Okay. So now we're going to switch the screen to somewhere within our platform. It's actually a URL you can try for yourself. So we will share a link in a bit later, so you can actually do the exploration yourself if you want. So what we're looking at here is one particular group of these groups, which we're kind of talking about, where we have matched 5 different things together. We've actually built 100 million of these, or even more, slightly more than 100 million of these groups. We did that in an automatic fashion. And so a group basically comprises a caption. You will see the caption, and then there will be one of each of the other modalities. So there will be a piece of audio. There will be a 3D model of in relation to that caption. So here we can see a boat. I hope you can kind of sense it here. There will also be an image relating to the caption, and there will be a video similarly relating to the caption. And with the dataset, of course, we have shared all the kind of relevant metadata you would expect. So, for instance, where everything came from, this audio file is from this particular dataset. The image is sourced from this dataset, and so on and so forth. We've also shared, based on how we build the dataset, how similar, as according to our models, each underlying piece of data is to the actual to the caption. So that is like what one of these things does. And yeah, so we took all these data points, all these groups, and then we trained an embedding model similar to Clip. So I thought it would also be pretty nice to actually see what that looks like. One way you can use it is by similarity search. So here I could search, for instance, for a construction being done on a road. So that we would take that piece of text, would embed it with our text component of our model, and then we would search all the embeddings from the other, against all these groups. So here you can see I can find these data groups where I have construction work going on. I can again go in and I can see the 3D model and everything. So I think this is like one pretty cool use case. We can take a few others if you want. Let's see. If I take an airplane taking off, for instance, I will see another part of the subset. So this is really what the dataset is, and there are a lot of different types of embeddings. I want to show a few more things before we jump back to the slides really quick. So I can also come here when I am exploring and look at the dataset from like a 2D perspective. So we have reduced the embeddings, and then you can see them here. I can color by different things. So for instance, I could color by the similarity between the point cloud object and the caption. Now it seems like there's a green region here with a high similarity. let's have a closer look at that. In here, there are also a few clusters. So let's just, for the sake of the exercise, let's view some of the data in the Explorer. And sure enough, here you'll see that this is a lot of tractors. And similarly, you can also say, oh, I really like this group, and then I can do similarity search. So all these embeddings are powered by actually training a model on the data. Yeah, you can also, if you want, I'm not going to go too deep into this, but you can also look at the individual underlying files, because we obviously sourced all this from different files, and you will also notice that some of them, they are sort of reoccurring in multiple groups. So you can also get a better understanding of that.
Nice. Really gives a sense as well of the breadth of data we've got in here, right? That, you know, I've been around and explored the embedding space myself, and there's tractors and planes, there's animals, there's people playing music, there's, you know, people playing sport, almost any kind of little video that you would find there on the internet, or sound clip or image. It's hiding in the embedding space somewhere, waiting to be found amongst those 100 million cases.
Yeah, one thing we should probably notice here is that in this exploration tool, you will not see the entire data set, and that's because of licenses. Some of the data is just like, it's meant for open source use, and it's not meant to be in a sort of commercial platform. So we are not allowed to show that. So we will, of course, refrain from that.
Yeah. And if someone wants to play around with this interface themselves, where should they go? Is it, I think it's data.encord.com?
Exactly.
Yeah. So yeah, if you go there, you can explore the data set yourself through this kind of interface, and also get a link to download it yourself, and that'll be downloading the whole thing, so you can start to do your own experiments or train your own models. Super. Cool. So now let's go into a bit more detail about what the data set is and how people can use it. And we're breaking that out in terms of 3 different workflows, 3 different parts of the journey of building and deploying a model: pre-training, post-training, and then evaluation as well. So Fred, tell us a little bit about the pre-training corpus that we have here.
Yeah. So again, it's 100 million paired groups. We did the pairing by taking these types of embedding models, like CLIP, one like the state-of-art model for every one of the modalities. So one model for point clouds, one for text, image and video, and one for audio. And then we sourced a lot of captions, almost 7 million captions. And based on these captions, we did similarity searches, or like natural language searches, across all these different modalities. And in that way, we were able to sort of group different modalities to the same caption, or with the same caption. And so that brings us to roughly 7 million. And then we, of course, took not only the first and best pair, but we actually took more than that. So we took 16 nearest neighbors per caption. So that's how we've built the data set. And there is, of course, a lot of technicalities into like how you do that in like an efficient manner, how you ensure all these different kind of hiccups you might expect to find when you are using these large scale data sets. And we'll get into that in a second. Yeah.
Nice. So let's also talk about how it was built operationally. It's no mean feat to acquire millions of video clips, millions of images, and audio samples as well. We can see the scale of the number of each modality's data points in here. Where are we sourcing this data from, and how do we ensure that the quality was high?
Yeah. So there are a couple of things we did. So first of all, we sourced this data from 13 different data sets. And for some modalities, there were more. For some, there were less data sets. You can probably infer that for 3D point clouds, there were less. And I would say if someone were to ask what is the limitation of this data set, that would probably be my first answer, right? Simply because that type of data is just more scarce. So we source data from a lot of open source data sets in the first place, and preferably open source data sets where they also had captions, because then we would kind of use them to link things. Not strictly required, because having a bigger pool of data to search from is still better. So that's how we sort of source the data. And then of course we had a lot of things we needed to do for videos. For instance, you need to make sure that you don't have these sort of funky formats or variable frame rates, corrupted files. We also made sure that to check for NSFW filtering. And then one thing we spend quite a lot of time on is actually filtering down the data set such that it doesn't contain any leakage to sort of known evaluation sets. That's one of these pains that many people and even like the open source community and academia has this problem right now for these types of models, that there's actually quite a lot of leakage at the moment. So we kind of made sure that was all right. And then of course I think we talked about the licenses as well.
So a lot of operational sort of safeguards that have to be built in there, a lot of manual work. I think we've got another poll now as well to ask those listening, which of those challenges matters most for your organization before using a training set, particularly an open source set that has been built by somebody else before it goes out there. Evaluation leakage, important for making sure your benchmarks are right. License and provenance to make sure that you don't get sued by the person who actually owns that data in the first place. Duplication, human review, making sure the data is not corrupt. Or if there's something else that's important to you as well, then please go ahead and flag that to us too. Fred, is there anything that people using this data set need to think about or need to worry about with respect to those operational controls, or has everything been taken care of already?
Yeah, that's a good question. There's of course always the licensing, and I also saw it showing up in the poll as well. There's always the licensing problem. So depending on what you're using the dataset for, you of course need to take care of licenses. And in the actual dataset release, so on GitHub where you can download the data, we actually share the license of all the different datasets that the underlying data came from. So our license for all the groups is completely open. You can use it both for commercial and non-commercial use. But the underlying files may have different licenses, so you have to maybe be a little bit careful there. But it should be pretty transparent.
Nice. And in terms of the quality of the pairings of the data set, how should people who are potentially using it think about that? Is there there are different sort of phases of their process that they should go through? Is there like manual work that people should undergo to do some verification for a particular use case they're planning on using the data set for, in your opinion?
Yeah, I mean, I think it mostly comes down to using the data for training and practice. So that means like figuring out what is the scale of the data you need. And I think we'll get back to this, but there are a few tricks for like how to select the right subset. Some of the tricks, I think I showed in the UI, that there are actually also associated similarity scores. So you have kind of an indication of how good is this particular piece of data for this particular caption, and that may be relevant. So you can filter down the data in that way. You can also filter by I was about to say rank, but basically how was it the nearest neighbor or the second nearest neighbor. So there are many ways in which you can sort of operationalize it. It should be such that all the data you download, if you download the subset that we have released, then it should be pretty good. Of course, URLs can disappear on the internet. That's hard to.
But that's why we've got millions and millions of them, right?
Yes.
Nice. Okay, let's talk about then the other artifacts that we've generated alongside the raw data set and how people can use those. So, we saw in the demo you gave a minute ago an ability to explore the embedding space related to the data set, but that embedding space means that we need some embeddings and we need an embedding model. So can you talk us through what we've built there, how you built it, and how people can use that?
Yes. So we really wanted to demonstrate the value of the data set. And I think a good way to do it is find the most vanilla implementation you can and show that it works better than most things. That's essentially what we're going for, and I think it worked out pretty well. So what we have done is we've taken three models, pre-trained models from elsewhere, one for audio and one for computer vision and one for 3D point clouds. And then we have embedded all the data, or all in for once, stored all the embeddings, and then we made a data loader that can load the embeddings, and then we trained a small projector on top of every one of them. And those projectors, they would put everything into the same space. So if you kind of fancy doing something similar where you don't want to run these big models, you can also just use these pre-computed embeddings and train something else on top of that. And there's a lot of headroom in terms of doing smarter things than we did. I'm sure that there are more people in the audience who could think of smarter things than we did, for sure. We tried to stay like very, very simple. And you can find that we wrote up a paper as well. You can find that in the release as well. But yeah, so these embeddings are also available, which means that you could just use these embeddings as an index and try to select the right data for your particular purpose if you want, or you could use it to train on top of.
Yeah, and the cool thing about these embeddings, right, is that we're mapping data from all these different modalities into one shared embedding space, which means that you can say, here's an audio clip, find me all of the 3D objects which are semantically similar to this audio clip, or here's a video, find me all of the pieces of text that are semantically similar, or whatever it might be.
Yeah.
And then, of course, exploring those groups of data in that same space as well. Super. So that's what we can do on the pre-training side. Let's talk now about post-training, what we've done there and how teams can use that. So I guess the first question is, how does the post-training data set differ from what we just saw, the pre-training data set?
Yeah. So maybe the first thing to think about is quality versus quantity. So the pre-training data set was really aiming for quantity, right? We wanted a lot of data where we could like really scale compute with the data. And the other thing is you need very high quality data to actually, so you kind of align, you align the model with this post-training data. So in order to be able to do that, you need to make sure that the data is really, really good. It has to be diverse. It has to like cover all the use cases you care about. It also has to be balanced in the sense that you don't want to have a lot of data from one particular, like when it's internet data, you don't want to have all the cats and dogs only, right?
Yep.
You want to have everything else as well. And that's kind of what this sort of figure is meant to illustrate, that we're kind of starting from this. So we took a subset of, we took the captions from the big data set, and then we had to select a subset to actually annotate with humans. So the first thing we did was we realized that, okay, there is actually this long tail of concepts. So we found a way to actually sample such that all these concepts, they become roughly uniformly distributed rather than this long tail. And then we use these retrieval models to group things. And when things were grouped, we showed them to humans to rate them. And why did we do that? Well, because if you want a system that is aligned with humans, at the end of the day, you need humans to actually say, this is what I care about, this is what I do not care about. Yeah. And so, yeah, we will also see in a bit how we actually like made sure that we were also aligned as humans. We'll get back to that in a second. But yeah, so then we would rate everything. Is this a good match? Is this a partial match, or is this a bad match? And this is very useful for stuff like hard negative mining. So this is a way of finding hard negatives, which is really, really fruitful especially for contrastive learning. Yeah.
Yep. And so, but by hard negatives there, you mean finding those cases where perhaps you might have thought that two pieces of data from different modalities were similar, but actually a human reviewer has come and said, no, there may be, they sort of seem similar, but they're actually different in an important way. And that's the kind of thing that your model might have otherwise got wrong because the retrieval, perhaps they're similar in the retrieved space or something like that.
Yes, exactly. Thanks for clarifying that. Another way of thinking about it is you want to find all the examples where the surprise is very high.
Yes.
Right? The model has to be surprised when it sees something. If everything is easy from the get-go, then it's not really going to learn anything new.
Yeah, and of course that's the value of human review in a sense. If the human reviewers totally agree with your original pre-training data set, there's nothing surprising there. They haven't added any value. So we need the human reviewers to be agreeing, but also disagreeing with what the similarity in the embedding space might suggest.
Yeah, exactly. Exactly. So, I mean, just before we go to the next slide, there are like these two red boxes, right? So the first is like this data bias, that you're biased towards some concepts that are more frequent on the internet. And we have one solution for that. And then there's another bias, which is basically these retrieval models. They have a bias in the sense that we like that's basically what we were just talking about.
Yeah.
They are so you can break that with humans.
Yeah. So 2 kinds of bias: data bias, and we're resolving that by making sure we're sampling correctly with the right distribution, with the right amount of data diversity, and then model bias, and we're addressing that by using that manual human review step to ensure the quality is there. So let's talk a little bit about that first part then, building diversity in the data set, how we can ensure that we're not accidentally taking some subsample of the pre-training data set that is biased in some way or missing some important section of the data. How do we do that?
Yeah. So if you look at the lower left corner of this this slide, and you think about that as a data set, these 5 circles, you can see some of the circles are very filled with a lot of points.
Yeah.
Some of them are very they're dense, and some of them are very scarce in the amount of data. And if you just sample uniformly at random from this data set, you'll get what you have to the right, which means you will still have 2 like more dense circles, and some of them will be like very underrepresented.
Yeah.
So there's a particular piece of work from Meta that allow you to do sampling where it's like a hierarchical clustering approach, where you get something similar to the top one. So I think that's a good way of illustrating what we're actually trying to do, and we kind of went with that approach. So that is for breaking this long tail, or like balancing the sampling. And the second thing we did was this model bias we were talking about, is that we realized that some of these models, they really favor a few different data points. And there are a few data points that are just like very likely to be in top 5 or top 3 in the retrieval part. And so to break that, you can actually formalize it as a max flow mean cost. I don't know if you remember that from computer science back in the day. I don't know if you ever saw it. It's just like a fun little observation. That's an algorithm from the 70s actually, that we were actually employing here, which basically makes sure that every piece of data that is not a caption is not repeated too many times, and you get sort of the best similarities while ensuring that property.
Nice. So to summarize there, the original data set is always going to be sort of, in some sense, weird and biased in some ways. It's very hard to build 100 million of anything without some sort of data bias, but we want to make sure that when we're sampling from it, we're not sampling uniformly and missing out on those rare cases. We're sampling evenly over the whole space, rather than in a way that's weighted towards where there's a higher density of data. And this is the approach that lets us do that.
Yes, exactly.
Exactly. Cool. And then the second step was the human verification, making sure that those similarities between different pieces of data from different modalities were actually sort of reflected the semantic similarity in the view of a person, not just in the view of the embedding space. So how do we build that workflow?
Yes, that's a good question. And this is one of these places where we are very, very careful. Because you can give a human a task and say, you have to tell if this caption matches that thing, or if this image matches that piece of audio. And then they will have 5 different ways of thinking about that problem, and they will have 5 different answers. So in order to get also the humans aligned to actually give the same types of annotations or answers to the question of, do these things align? We had this flow that is set up here. So if you look from the left, you have this start node, and then the data flows into an annotation stage, and we will have a human annotate the pairing or rate the pairing, and then we will take the task and move it through this task router. And the task router makes sure that we internally in the ML team, we see at least 5 samples from every annotator. And if something seems off, then we will give that feedback. That's the lower red edge back to the annotator, and they will annotate it again. And so once we reach a stage where we're happy with every one of the annotators, we'll shift the review to another team that is not the ML team. That has to be, like, I guess the ML team has to be the most obsessed with the data at the end of the day. So someone who is, I guess, who can take over the rest of the review, and then eventually, when you kind of agree with the person, then you can let things go through to complete directly. That's the uppermost, I guess, auto approve in the task router. So really 3 tiers of evaluation. Very careful from the ML team, cheaper from the workforce, and then finally just auto approve.
And although we're not here to sell the Encord product, worth flagging, this is a workflow you built in the platform, right? Those different stages of human annotation and this workflow graph, something that you could build and direct and implement using Encord. So nice call out there.
Yeah.
Nice. Let's talk about then what we sort of ended up with and evaluating quality.
Yes. So we ended up with roughly 1 million of these ratings of data. This counts both the good matches, the partial matches, and the bad matches. And they are distributed across 4 different types. So the green one, for instance, is between image and 3D objects or 3D point clouds, where we have like roughly 250,000 of these ratings, where people were given either a caption from an image and then rating a 3D object, or a caption from a 3D object and rating an image against that caption. And similarly for audio and image, and for audio and 3D, the blue one, and for video and 3D, the purple one. And I think one of the things that is interesting to observe here is, also in the interest of time, I'm a bit short on the answer here. One of the things that is interesting to we observed while building this data set was that when doing this, there's actually no data at all out there between audio and 3D points. So we didn't even have a way to evaluate our model on the task of finding audio from 3D points or vice versa. So we actually had to build on top of this. We had to do even more annotations for building like a very, very high quality evaluation data set as well.
Yeah. So that's the challenge of being first, right? There's no one there to have built a nice evaluation benchmark to go and use to make sure things are working. You've got to do it yourself.
Yeah.
Nice. Let's talk about evaluations then. Finally, how do we evaluate the quality of that human review process and make sure that the data sets we've ended up with are at the level we want them to be?
Yeah. I think we talked a bit about in the very beginning about zero-shot classification. There was this thing where we were embedding text and we were classifying images, for instance, based on these embedding similarities. So we adopted a similar approach here, where you embed, for instance, a piece of audio, and then you have an object representative from more than 100 different classes. And then you have to classify the audio based on the embeddings of the representatives. And you can do that vice versa. So that's the task. And how do you build a data set for that? Well, we took roughly 1,800 data points from audio and roughly 1,800 data points from point clouds. And then we matched them up against more than 100 different classes. So we bucketed things such that we knew that everything from these within each class was only from that class. And we did that in a human consensus way. So now we didn't only have one person looking at a pair and verifying that it was okay. We had multiple people actually looking at the data, ensuring that there was complete consensus on this pair is correct. And only then we would include it in the test set. And again, this was, we don't have the figure here, but again, this was one of these things where it's really nice to work at a data company, where you can just set these things up and it just kind of works. You know how to control workforces and these kind of things.
Nice. And then talk about the sort of baselines that we were measuring against, and what's the delta that you saw over those baselines?
Absolutely. So I kind of bragged a bit in previously that it actually does pretty well, and I still think it does. If you look at this graph, on the x-axis we have the model size, and if you look at all these scaling laws there are, for instance, for LLMs, you typically expect more performance with a bigger model. That's also what we see here, but we also see this law of diminishing returns, that you cannot just scale and then expect a linear increase. It'll sort of drop off the performance increase. And then on the y-axis, you have the performance. So we wanted to make something that was really scalable in terms of inference. We wanted to make something that we can actually employ and embed a lot of data. So we kind of restricted ourselves to a rather small model, and then we really obsessed about the data. And the orange dot here is what we get when we average over 13 different performance metrics across all these 5 different modalities. So yeah, if I were to say myself, I think it's pretty nice to see that you can really like trump compute with good data.
So the takeaway for people potentially interested in using the model, so that orange dot is us, and the purple dots are other models available out there for multimodal embeddings. And we focused on a smaller model that with a high quality data set can achieve performance that is pretty close to the much larger, much harder to deploy, much more expensive, much slower models out there as well. So hopefully that's useful for people who are looking to actually deploy these multimodal embedding models in production and get a high performance. And that average performance there, that's our sort of average across all of these different benchmarks and different modalities, right? Nice. Okay, so I think that takes us more or less to the end of the webinar today. I suppose the most important thing for anyone listening to do if they found this interesting and want to explore the data set further is to go to data.encord.com, and you'll be in exactly the same demo environment that Fred was in when he was exploring the data set earlier. You can do natural language searches and find pieces of data that might be interesting to you. You can explore the embedding space and see those different groups of multimodal data as well. And then you can also go further and go and download the whole thing so that you can run your own evaluations using our benchmarks, so that you can go and train your own models on our data set. And even though it sounds a bit strange, I think Fred would be very happy if you can take that data set and go and beat the performance that him and his team managed to build there. Our goal here is to provide the foundations for other people in the community in the open source world to continue to improve on their ability to train multimodal models and build cool applications using that data set that just didn't exist there before.
Yeah, one little tease I can maybe add as well is that we are currently thinking about how we can take this data set and actually make it multilingual as well, so it doesn't have to be English, all of it. So that's one of these things we hope will be coming in not too far of a future. Yeah.
Nice. So in our last few minutes, maybe we can answer some of the questions from the audience there as well. So let's take this question from Annabelle. So human raters probably disagree with each other sometimes. Do you expose in some way the disagreement scores in the data set so that someone who's using it can like filter based on whether there was consensus or not consensus amongst the annotators?
This is a really good question. For the post-training data set, there's one rating per data item, so there's no consensus there. But for the evaluation set, we filtered it down to all the stuff that is only top, like 100% consensus. We could definitely release the other annotations as well. That would be that would definitely be possible. One thing to notice is that all this data is evaluation data, so it's not something you can train on. So,
And then a question from Anna. She asks, how did you make sure that the embedding spaces are aligned across all 5 modalities and not just pairwise?
Yeah, that's a good question. And actually the assumption is quite nice. So I assume you did not use only pairwise alignment.
Yeah.
And it turns out you can actually use just pairwise alignment to a large extent. And then you just have to mix your data correctly. So mix batches of different modalities. So you not only see images all the time and then audio all the time, but if you mix them, then you can actually I think it's more or less equivalent probably to mixing batches. But yeah, you can do it with a very simple loss function. It's in the paper. You can find it in the GitHub repo.
Nice. That's a good call out. So if you go to the link here, data.encord.com, you can also find the GitHub repo with the data. It also has a paper that describes in a lot more detail the process for building the data set and how it can be used. And then maybe just the last couple of questions. So we had one from Chris has just come in. How do you detect time-based drift between video and audio? Yes. So what's the false positive rate here?
That's an interesting question. I think Time-based drift is, so we match video and audio on content. We don't match. So it's like if you're thinking about lip syncing, for instance, that's not what we do in this data set.
Because the audio, it's sort of audio and video that are two different clips, but semantically similar. But it's not like the audio is the audio from the same video clip.
Yeah. If we
Yeah,
were looking for that, we would have to take just the video, I guess, and this audio.
Exactly. Yeah. And then maybe just last one, and then we can leave it there for today. So, last question is: if we operate in a regulated domain, what extra metadata or procedures would you recommend before using this data for training?
Yeah, it's a good question. One of the things I think would be pretty cool is you can actually build your own sort of index of other, let's say, regulated data, and then you can match it up against our data, and in that way you can sort of maybe like proliferate your own sort of more restricted data set based on our data. It doesn't require metadata per se, but it requires you to have some way of embedding your data and matching it against ours. So I think that's basically the work we did on the research side here kind of indicates at least that you can do that, and you can win from including more of our data. But yeah, I think for these regulated domains, it's very interesting to think about how you take data which is free for use and then use it to improve your models. Very interesting question.
Nice. Cool. I think we're out of time for today, so we're going to leave it there. But again, call out, please have a look at the dataset, data.encord.com. You can explore it there. You can read the paper. You can download the whole thing as well. So any extra questions that anybody had, hopefully they're either answered there, or you can always get in touch with the team afterwards by following that link. So thanks again, Fred, for your time, for your team's time for today, but also actually the work you've done over the last few months to build this data set. Hopefully it's something that the open source community and lots of other people find really valuable. And hopefully it's just the first of many. I can see there it's EMM1. So there's always room to continue to grow and improve it.
Absolutely. Thanks for having me and taking me, comfortably through the conversation. It's good to have someone to sort of take a step back.
Yeah. Well, thanks very much everyone for joining as well. We'll see you next time. Bye now.